Hey everyone, I'm Shee. I work for a company called Seldon, and today I'm going to talk to you about optimizing inference for state-of-the-art Python models. A bit of a kind of lengthy title, a little bit confusing, but let's just recap what we're actually going to cover. So to start with, I'm going to cover the challenges of building your own inference servers. This is something I see all the time with ML engineers and data scientists. And my personal opinion is that you should not be doing it. And hopefully I'll win you over by the end of this presentation. The second thing I'll do is I'll introduce an open source alternative and show you some of the cool things you can do within that. Then we'll look at serving some state-of-the-art models. We're going to use Hugging Face in this example. And then we'll look at some techniques to reduce infrastructure usage and latency. So it's really about like optimizing those models that we're running and making sure we're getting the most like bang for our buck from our infrastructure. Okay, so those are the things we're going to cover. And then finally, what I'll do at the end is just wrap that up with saying a few words about like when we get to production, what are the best practices for how we do that? Okay, so I mentioned at the beginning, right, that one of my motivations for this talk is to try and convince people to stop building their own inference servers. If you look at this code sample on the left-hand side, right, I'm sure lots of you will be very familiar. What we have here is just a simple Flask API endpoint, right? And you can see I've kind of implemented this predict function. And within there, I can put all sorts of Python logic for serving my machine learning model. Now, there's nothing wrong with this approach, right? It's just to say, hey, my model is written in Python. Let's put an endpoint in and just write some Python logic in it. But there are a lot of challenges that come with this. It may work really nicely at first just to get something up and running. But as you start to build more and more models and you start to roll these into production, there are challenges you're going to come across. So let's look at what those are. The first of these is that the infrastructure you use is like going to become more and more important. Sure, when you're testing your model locally or when you're running something once and you want to see how it is, that's fine. But as these start to scale and as you start to roll out more and more models, suddenly your cloud costs might go through the roof. And we have to become, more and more aware of that. The second one is dependency management. So, writing your own app, whether it's Flask or Fast API or whatever, right, seems easy enough, right, to just bundle all your dependencies in. That's okay for you as the user, but for the, potentially other person in your company or organization who has to deal with that in production and deploy it, they might be given a ton of different Python Flask apps by a bunch of different data scientists, all that have different dependencies and all that need serving in a slightly different way. So that then becomes a real headache. The third one is that we need to be able to work with multiple machine learning frameworks. Sure, there are some companies out there who maybe just pick one and do, you say like, we do everything in PyTorch, and there's, that's fine. But probably the vast majority of companies are using a mix, whether it be scikit-learn, XGBoost, TensorFlow, etc. What you really want to do is allow the data scientist to have that choice to use whatever machine learning framework either they're comfortable with or they think is suitable for tackling the task that they're trying to achieve. But you also still want to be able to serve these in the same way. Another big one that comes up is like standardizing those API definitions. So if I'm actually just going to jump back again. But if we look here, you can see I've created this very simple machine learning code on this /predict route, right? Let's say, someone else in my company creates their own Flask app with their machine learning code in it, but they put it on /infer, right? And someone else puts it on, /API/version/predict or predictions, or, you can see how very quickly this becomes quite messy. We don't know what the route is that we're going to expect to hit in order to get predictions back. So we need to be able to standardize on that. Something that I'll come onto in a little bit is an effort that we've had at Seldon in collaboration with other companies to try and build an open inference protocol around that. And then capturing the payload structures becomes really important. So if it's, again, fine if I'm the data scientist who built the model, because I understand the inputs and outputs. But if I'm the end user who, realistically, if you're turning it into an API, is probably going to be some developer at your company. That developer has to interact with that API, and they need to know, what are the required inputs? What are the outputs going to look like? How do we give them that information without either writing tons of documentation around it, or having to have that conversation one-to-one with every user who wants to use your API? So being able to capture the metadata around that and provide it alongside the model becomes really important. And then finally, just looking at like the multiple versioning of models, how do we roll out new ones? How do we replace the existing ones? Can we roll things out and test them and, do A/B tests and things like that? So these are all the kind of things that you're going to start worrying about. What I'm going to show in the hands-on examples today is an open source library called MLServer. So it's built by the team here at Seldon, but it's used in a wide array of other frameworks around that you'll find around the web, all for machine learning serving. And MLServer is a Python-based inference server. So as I mentioned, it's fully open source. And the idea is it's designed to serve machine learning models. But what it actually does is it serves these over both REST and gRPC. So that's, again, another benefit, right? If I've just written my Flask code back there, I can't access this over gRPC, which we know performs much better and is much lower latency, particularly at high throughputs. And then the other thing that MLServer does is it supports all of the popular Python-based ML frameworks. So, if you want to run an ML flow model, you can run it with MLServer. If you want to run Hugging Face, Runtime, XGBoost, etc. In terms of the way it works, right, there are like a couple of things you need to provide to the MLServer library. The first is this settings.json, and this is just the config for the actual server itself. And then the second one is a model settings.json, and this is the model specific config. So for each model that you might want to serve, you need to provide a little bit of configuration around what it is and how to access it and how to serve it, etc. One of the really neat things within MLServer is that you can do multiple models served on the same instance of MLServer. So if we look at like how traditionally it works, on the left-hand side here, we can see, when I deploy a model, I kind of wrap it up with either the Inference server or the Flask code and all the dependencies or whatever, and we run it as a single standalone server, or it might run in a single container. And then I deploy another model and I do the same thing. And I deploy another model. And you can see that each of these have overhead associated with them. There's the framework. Let's say, if it's a TensorFlow model, if they're lightweight TensorFlow models, TensorFlow is a pretty heavyweight runtime. And actually, you might find that like the vast majority of your infrastructure usage is just the framework overhead for those lightweight models. But if you want to run 4 of them, you've got to run that framework 4 times. So with multi-model serving, which is something that MLServer supports, what you can do is you can run all of these different models all within the same container. So that way you only have one set of overheads, which is the kind of framework. In my example, it might be TensorFlow, and I might be able to serve all 4 of these models from that same set of TensorFlow dependencies. What I'll do is I'll dive in and show some of this because I think it kind of makes it all a little bit more interesting. So what I'm going to show you quickly is, imagine I've trained a very, very simple machine learning model. In fact, we can have a look at that. So here's the training code. Hopefully, my job here is not to teach you how to do machine learning. Hopefully people know that already. But if you look through here, you've probably seen a very simple example like this before with scikit-learn. I'm going to pull in the fashion MNIST data set, and then I'm going to train support vector machine. And then I am just going to save that classifier as this fashion MNIST.job lib file. So I'm doing a quick, save and then, classify fit and then saving it. And I've actually already done that. And you can see the pickled object sitting here already. And then what I can do once I've trained and saved a model is I can serve that with MLServer. So let me just do that. And I can run MLServer start, and you'll see that it's run that up immediately. And you can see right at the bottom here, it's saying loaded model, fashion, sklearn. So let's just take a look quickly at that model settings, because this is the thing I mentioned that you need to provide to the server for it to know how to serve a model. So very simply, what I've done here is I've given my model name, and then I've given it the implementation. And the implementation is basically telling MLServer, what type of model is this? And there are a bunch of these kind of out of the box implementations for things like scikit-learn, XGBoost, Hugging Face, etc. And then I'm giving it what's the actual URI of my model, and I'm saying, here it is. It's just in that job.lib file that I just saved, and I can additionally give it version numbers. And if I wanted, I can put all sorts of metadata in here. This is just showing you how you create a very simple one. Now that's all I need, right? Once I've got that model settings file, I can run MLServer, and it will go, okay, cool, brilliant. I'm going to pick that model artifact up, turn it into an API that's now ready to accept gRPC and REST traffic. And actually, we can test that really quickly. We'll just use this very simple test script. You can see I'm pulling down the test set from the fashion MNIST data set, and then I'm going to build myself an inference request, and then I'm going to fire it off to my local host, which is where that classifier is now running. So let's run that. Yeah. All right, and you can see what happens. Actually, let me make that a bit more readable. Okay, so we get our prediction back. Our data here is classifying this one as class 0, whatever item of clothing that relates to from the fashion in this data set, we could go and look up. But you can see that my MLServer has received these 2 responses that we just fired at it. So that's how I can serve a simple scikit-learn model really easily. Now let's stop MLServer, and let's say in my world, I wanted to see, like, if I train an XGBoost model with the same data set, will it perform better? So let's just go to that one. Move around here. And then you'll see in my XGBoost folder a very similar thing. Again, we can look at the training code here, and you'll see it's almost exactly the same. This time I'm going to train an XGBoost model here, and I'm going to save it as this fashionmnist.json object. And then what I'm going to need to do in my model settings is I'm going to tell, that's my scikit-learn one. Hang on. Let me kill this one, because otherwise I'll confuse people with let's look at just the XGBoost one. So the XGBoost model settings here, you can see I provided that URI fashionmnist.json, right? And this time I've changed my implementation to XGBoost. So again, that's all I need to do. Give it the model artifact, tell it what type of model it is, and give it a name. And then I can say, okay, MLServer start, right? And off it goes. Okay, cool. So in just a second, that should say, yeah, it's loaded my model. And we could equally do the same thing here where we go, Python test, run a test inference request, and we'll see that we're getting responses back. So you've seen how easily I can serve different types of model. But what's even cooler is the fact that we can serve both of these at once. So if I go, let's go up a bit, and then let me just show you what this looks like. So I'll show you what my repository looks like here. I've basically got this, like, what might be my ML project, right? I've got in my models folder, I've got my scikit-learn one and XGBoost one. Within each of those, I've got my training and test code and each of the artifacts that get saved. So this job.lib and this JSON file. And then finally, I've got this settings.json, which is the server settings that I might want to run in my base repository. Now, the cool thing that MLServer does is if you just start it in any repository, it will search through the tree of underlying folders and look for these model settings.json files. And if for any of those it finds, it will serve those models. So essentially, if you put them in a folder structure like this, where you've got multiple folders with different models in, and then you'd say MLServer start like this, it will bind those models and serve all of them at once. And you can see this down at the bottom. It's saying, loaded model fashion XGBoost and fashion sklearn. So they both got loaded onto the same inference server that's running here. Okay. And then finally, let's do just check that that's running. We can run inference request against both of them. So we could do like this test models. And you'll see what's happened there is it's fired a bunch of a batch against each the XGBoost and the scikit-learn model, and it's come back with like an accuracy score for them from the live inference server. And we can see our XGBoost model did perform slightly better. Okay, so that gives you an idea of how the kind of multiple model serving aspect of it works. I'm just going to jump back in for a second and talk about a couple of other things that are really neat within MLServer. The first of these is parallel inference. So what MLServer will do is it can spin your inference runtimes up on individual workers, which allow you to like bypass the inherently single-threaded nature of Python. So let's say you're running inference on a machine that has like 4 cores, but because of the blocking nature of Python, those inference requests are probably only going to get handled on one of them. What MLServer will do is spin that up on 4 different workers, like you're seeing in this example here on the right-hand side, so that as those requests come in, they can get passed to individual workers, these separate Python processes running on each of the cores that allow you to maximize the use of the CPU in this case. Another really neat thing that it does is adaptive batching. And I'm actually going to show this as part of a demo because I think it's nicer when you get to see how well it performs. So let's just, again, stop MLServer over here. And then we're going to go, just going to move into a different repository here. And then let's clear these so you can see what's going on. And then I'm just going to change Conda environment as well. Okay, cool. So what I've got in this repo, let me again open this so you can see what's going on, is one of the really cool things with MLServer is you have this Hugging Face runtime. In fact, get rid of that. We'll talk about the adaptive batching in a second. We have this Hugging Face runtime that allows you to pull models directly from the Hugging Face hub so that you don't actually have to provide the inference artifact at all. So you'll notice in my folder here, I've got, if I look here, all I've got is like a couple of Python files. I've got this load.txt. I'll come back to that. That's going to be for a load test that we do in a second. And then I've got my model settings. There's no inference artifact here at all. But what I can do is I can tell MLServer, well, I want this Hugging Face model. And then I give it this extra parameter here where I say, I want the task to be text generation. I want this pre-trained model called still GPT-2, which is a kind of smaller and optimized version of GPT-2. And then I can also tell it some other things. Like in this scenario, I'm actually going to tell it to use my GPU here. So specifying device 0, because if any of you played with this, it takes a long time to do text generation on a CPU. And I don't want you to have to sit around and wait whilst I do it. And that's basically all I need to give to MLServer is this model settings for it to be able to go and serve stuff directly from the Hugging Face hub, either locally or potentially in the cloud if you're running MLServer there. So let's start one of these up. Okay, and then we'll take a second because it's going to pull the model and then load it into memory and start it. And it's a decent sized model. One thing I mentioned whilst I'm in here is the piece that I've just taken away. In fact, I won't. I'll come back to that in a second. So what I'll do is whilst this starts up, I'll talk about what we're going to do next. So rather than just sending a single inference request, I wanted to show like performance benefits of doing adaptive batching. Now, what is adaptive batching? I'll explain that with a diagram because I think that's the easiest way to show it. But what I'm going to do is I'm going to fire a load test at this model where I say, please, can you generate me a bunch of different text, but I'm going to send 50 requests. And you can see here with this rate, 50 of these, and I'm going to send it for 3 seconds. So basically I'm sending 150 inference requests really quickly over 3 seconds at my model to see how well it performs. And that's for a text generation task, that's quite a lot. So we can see this model has now successfully loaded. Let's do that. What do I call it? Okay, so let's run that load test. And what you'll see down this left-hand side is that MLServer is handling each one of these requests as they come in. It's generating text through the distilled GPT-2 model, and then it's returning all the responses back to my load test workers that I've just fired up in this other terminal on the right. And if we give that a second, what we'll see is some results on the other end. Okay, so what you'll see here is that, let's look on the right-hand side here. So I'll try and highlight the important bits. Let me make this a bit bigger. Oh, maybe too big. All right, let me make that full screen instead. You can see. So what happened was I sent across the top here the requests. I sent 150 requests, 50 of them per second. So the throughput was kind of 2.3 because not all of them succeeded. And the important bit here is the whole thing took 32 seconds. Right, so remember that because we're going to come back and compare that to the adaptive batching when we turn that on. And you'll see the other thing is that actually only 50% of those requests succeeded. So with the 150 text generation requests, like half of them made it through. The rest of them probably timed out because there's a 30-second timeout on the server that we've set up. So that shows you, right, it's not ideal. These are not great results. So what we can do in MLServer, we can set this setting here called max batch size and max batch time, right? What are those? Okay, the easiest way for me to explain that is to show you it via a graphic. So I'll just start that one up and let it load and then jump into my slides again. Okay, so what is adaptive batching and how does it work? Well, as you saw with my previous requests as they were coming in, we're getting this like inference request, but there's only like one training record in each of those. That's not an optimal way for my machine learning model to be doing inference, right? The way adaptive batching works is that as these requests come in, it collects them together into a batch and then fires that batch payload into the actual inference runtime so that we can, execute predictions on a batch of a potentially variable size each time. And then on the other end, it unbatches these and then returns them as responses to each of the requests that have come in. So you can see here on this, left-hand side, I've got 3 requests coming in, then they're batched together, they get run through as a batch, and then they unbatched and sent back again. The parameters that I'd set up here, so the first one is like the maximum the number of requests I can put into a single batch. And the second one is like, what's the maximum duration before I batch them together? Because what we don't want to do is wait like 10 seconds until we've reached 128 requests to batch them all together, because it means, the first request might have to wait 10 seconds plus some. So here I'm setting, the maximum time to be 1 second. Okay, and if we see how this performs, what we'll do is let's go and run that same load test. It's a bit smaller. See what's going on. But this time, you'll see on the left-hand side that you can actually see visually these batches are being fired through. So as it gets these requests in like super fast succession, MLServer's automatically grouping those into batches, firing those through the inference runtime, and then debatching them on the other side and sending them back. And if I go and look at my results now, again, let's make that a bit bigger, you'll see 150 requests this time only took 9.9 seconds. 100% of them succeeded. So it's taken like a third, maybe more, because only half of them actually succeeded earlier. Now they're all succeeding, and it's taken a third of the time. So the adaptive batching really does like kick up the performance improvement massively. Cool. Right. So I'll jump back into the slides. Hopefully that's given you a bit of overview and intuition as to how adaptive batching works and why you should do it and how it drastically improves performance in certain situations. I'm just going to talk a little bit about model deployment. So everything I've shown you here has been running locally, which is great. MLServer as a Python library, you can just run it standalone on your machine. But what happens when you actually want to, package this up and run it in production? So the first thing is we offer this like MLServer build command. So you can just say MLServer build and then tag it, and it will automatically build this Docker image with the inference runtimes and your inference artifact into it, etc. And then from there, MLServer integrates to a bunch of like deployment frameworks. So this example on the left is using Seldon core, but you can also package these up and run them with KServe or something like that to deploy these machine learning models on top of Kubernetes through an orchestration framework. And that's something I always highly recommend, is that like you don't just deploy these as endpoints, because whilst MLServer takes care of the execution of inference and optimizing that, what it doesn't do is look after your estate of machine learning models, reconcile which ones are online. If the machine falls over, MLServer falls over, right? What you really need is like a layer on top of that, whether it be, something like KServe or Seldon core, that is going to, when your MLServer or your machine falls over, it's going to redeploy that to a different host. Okay. So it's been a lot to go through. I appreciate I've gone super fast and I tried to show some things as we went along. But if you take nothing else away from this, let's make sure it's these few points at the end. So the first is like, don't build an inference server unless you really have to. There will be, scenarios where you have to. Another thing to note is that even if you're writing like custom Python logic and non-standard models, there's a way even within MLServer to write custom code and still build it with MLServer. And you get all the benefits of things like adaptive batching and automated metrics and things like that. Don't build your own one, right? Use MLServer for Python things. Triton's a really popular one that people use for things like TensorFlow and PyTorch models. Multi-model serving as a technique is really good. It can save on infrastructure costs, particularly if you have lots of lightweight models. Adaptive batching, as we saw in the example, like drastically improves performance. But again, it slightly depends, right? If you get one large batch of requests every 2 minutes, it's not massively going to help. But in the scenario I showed you where you're getting lots of little individual requests, adaptive batching makes a huge performance increase. And then finally, use an orchestration framework when you get to production. Even if you're using MLServer, don't just leave it on its own, right? Have some sort of layer that sits over the top and manages it and make sure that your whole machine learning estate is up and running. And that was about it, right? I'm Shee, as I mentioned. I work at Seldon. You can find me on our Slack or on MLOps community or a bunch of other places. Feel free to email me or reach out on LinkedIn or whatever. And thank you for your time.